Okay, let's continue with sections 11.5. Okay, alternating series test. Okay. Okay. So let's do another example here. Example 3. Okay. Is the series the summation n equals 1 to infinity of -1 to the nth power 3n all over 4n minus 1, is that convergent? Okay, we want to see, does this thing converge? Okay. So we have two conditions, right? We need to know if bn plus 1 is less than or equal to bn for all n, and 2, if the limit as n goes to infinity of bn, okay, equals 0. Okay, now, let's test these independently. Okay, for one, if I take 3n over 4n minus 1, and I do n plus 1, that's going to be 3n plus 1 parentheses, 4n plus 1 parentheses minus 1. I want to know if that's less than or equal to 3n over 4n minus 1. Okay, and once again, I'm going to use the trick of cross multiplying here. Okay, and I'm going to get 3 times n plus 1 times 4n minus 1 is less than or equal to 3n times 4n plus 1 minus 1. So that's like that. Okay, so I'm going to distribute. This becomes 3 times n, 4n squared plus 4n minus n minus 1 is less than or equal to 3n times 4n plus 4 minus 1. Okay, so just continue to distribute. This is 12n squared plus 12, and actually let's combine this. 4n minus 1 minus n, this is going to be 3 times 4n squared plus 3n minus 1, okay. And now let's distribute. This is 12n squared plus 9n minus 3. Okay, and then this is going to be 12, and this is 4 minus 1, so that becomes 3n times 4n plus 3. Okay, and so let's distribute. That becomes 12n squared plus 9n. And that's it. Okay, and so yeah, I can subtract off the 12n squared and subtract off the 9n, and I get -3 is less than or equal to 0. Well, when is that true? That's always true. It's not dependent on n at all. So that's always true. So the first condition is satisfied. What about the second condition? The limit as n goes to infinity of 3n over 4n minus 1 does that equal 0? And the answer is no. If I do some algebra here, this is the limit as n goes to infinity of 3n over n all over 4n minus 1 over n is equal to 3 over 4 minus 1 over n. There's a limit there. Okay, and so when I plug this in, that goes to 0, and so the whole thing goes to 3/4, which is not equal to 0. So the terms are not decreasing. And so okay, so this actually diverges. Okay, so this diverges. It doesn't diverge by the alternating series test. The alternating series test is a test for convergence. Okay, this diverges how? Why does this diverge? This diverges by the divergence test. Because if the terms don't go to 0, then the series diverges. Okay, by the divergence test, the series. Right, let's say divergence test. The series diverges. Okay, because the divergence test is kind of snuck in there. You know, to the alternating series test. It says, hey, you know what? If it goes to 0 and it alternates, and all the terms are decreasing, then it converges. But if we get something that doesn't equal 0, then that is the divergence test, and it diverges. Okay. Okay, just like with the integral test, we can estimate how close we are with an alternating series. Okay, we have the alternating series estimation theorem. If S is equal to the summation of -1 to the n minus 1 b sub n, if that's my alternating series, where b sub n is greater than 0, okay, b sub n plus 1 is less than or equal to b sub n, and the limit as n goes to infinity of b sub n equals 0, basically saying that if this thing converges, okay, thus a convergent alternating series, okay, if all these are true, then the remainder of the nth partial sum is equal to the sum minus S sub n, okay, that's the definition of remainder, okay, which is less than or equal to the b to the n plus 1 term. Okay, so this is a little nicer than the integral. We don't have to take the integral series estimation. We just need to calculate the n plus 1th term. Okay, and we just need to make sure that the thing is going to go to it's going to converge first. We just need to make sure it converges, and then if it converges, we can find you know, some sort of accuracy of what it converges to. Okay, so let's look at number 4. find the sum of the series summation n equals 0 to infinity of -1 to the nth over n factorial. Okay, so this isn't the alternating harmonic. This has a factorial. And we want to find the sum of the series correct to 3 decimal places. Okay. Okay, so we need to find out, well, where is the, which term is going to give me, something that's less than 3 decimal places. Okay. Smaller than the first 3 decimal places. Okay. So I need something that's, basically less than 0.001. Okay. So is that true? Yeah, I mean 0.00. Yeah. For 3 decimal places. Yeah, makes sense. Okay. So I want bn plus 1 to be less than 0.001. Okay, so all I have to do is start calculating some terms. So 1 over 1 factorial. So this is b1 is 1 over 1 factorial. b2 is 1 over 2 factorial. b3 is 1 over 3 factorial. b4 is 1 over 4 factorial. Okay, b5 is 1 over 5 factorial. b6 is 1 over 6 factorial. And b7 is 1 over 7 factorial. Okay, and b8 is 1 over 8 factorial. Okay, so now this is just 1. This is 1/2. b2 is 1/2, which is 0.5. This is 1/6, which is about 0.16 forever. Okay, and this is 1 over 24, which is 0.0416 forever. Okay, this is 1 over 120, which is 0.0083 forever. Okay, and this is B6 is 1 over 720, which is 0.00138 forever. And then B7 is 1 over 5040, which is 0.000198. And so here we're now less than 3 decimal place accuracy. We're less than 0.001. Okay, here. And so we don't even have to go to the 8th. Okay, because we've hit, if we add something that is 2,000, no, not 2,000s, 2 10,000s, then that's not going to change my decimal, my first 3 decimal places. Okay, and so if I were to look at the original alternating series, okay, we're starting at n equals 0. Okay, so how does starting at n equals 0 change things? Let's not start at n equals 0. Let's back this out to n equals 1 and then n minus 1. There. That's better. It makes me happier. Okay. So yeah. Okay, then we get 1, okay, minus 1/2 plus 1/6 minus 1/24 plus 1/120 minus 1/720 plus 1/5040. So what do we want? Well, we don't want to add that one. Okay, we only want the first 6 terms. We want S sub 6, right? We're only allowed to go S sub 6, okay, is within, because that S minus S sub 6, okay, S minus S sub 6, okay, that is going to be equal to my remainder, which is less than B of 7, okay? It's N plus 1. B N plus 1 has to be. So if I go to B7 and it's less than the decimal place accuracy that I want, okay, then I back it out one term to S sub 6, and that is approximately to 3 decimal places. What? Let's bring up the calculator real quick. Okay, so we want 1 minus 1 divided by 2 plus 1 divided by 6 minus 1 divided by 24 plus 1 divided by 120 minus 1 divided by 720. And I'm getting 1 minus 1/2 plus 1/6 minus 1/24 plus 1 minus, I'm getting 0.6 32, 0.632. Okay. Now, if I add another, term here, what happens? If I add B7, which is 1 divided by 5040, okay, yeah, I get 0.6321, and it's still 0.632. And if I were to continue to add terms, I would have locked in the first 3 decimals. Okay, so S sub 6 is approximately 0.632. Okay, and that finishes up 11.5. Okay, 11.6 is on absolute convergence. And the ratio and root tests. Okay, so absolute convergence and the ratio and root tests. Okay, so definition. Okay, a series, okay, summation of A sub n is absolutely convergent . if the series of the absolute values summation of absolute value base of n is convergent. Okay, so some series are convergent and some series have this extra ability to be absolutely convergent. Okay. Okay. For example, number one, we know that the harmonic series is divergent, right? Okay. But the alternating harmonic series is convergent. Okay, and so okay, the series summation n equals 1 to infinity of -1 to the n minus 1, 1 over n is convergent by the alternating series test. But the absolute value of all of the terms, the absolute value of -1 to the n minus 1 of 1 over n, okay, as n equals 1 to infinity, is equal to n equals 1 to infinity of just 1 over n. Okay, by absolute valuing every single term, we get rid of the alternating part. Okay, which we know is the harmonic series, and so is divergent. Okay, thus the series is not absolutely convergent, okay. We call something that is convergent but not absolutely convergent conditionally convergent. Okay, it's conditionally convergent. Okay, if it is convergent but not absolutely convergent, then it's conditionally convergent. Okay. Okay. So let me draw kind of a Venn diagram here. Okay. So outside of the Venn diagram, we have divergent. Okay. So these are things that are divergent. Okay, inside we have things that are convergent. And inside that, we have things that are absolutely convergent. Okay, so absolutely convergent is a stricter convergence. Okay, if something is absolutely convergent, then it implies that the original was convergent itself. Okay, so if we can get absolute convergence, then we know that the original was convergent, even if it alternated. Okay, absolute convergence is stricter than alternating or than just convergent. Okay, but if something's convergent, that does not imply absolutely convergent, because it could be either absolutely convergent if the absolute values converge, or it could be conditionally convergent okay, it's absolutely convergent if the absolute value of a sub n converges. And it's conditionally convergent if the absolute value of a sub n diverges. Okay, like we saw in the previous example here. Whoops. Okay, let's look at one that is absolutely convergent. Number 2 here. Okay, the series, okay, test, I'll ask a question. Is the series summation of n equals 1 to infinity of negative 1 to the n minus 1 of 1 over n squared is that thing absolutely convergent, conditionally convergent, or divergent? Okay, is the thing absolutely convergent, conditionally convergent, or divergent? Okay. Okay, so we don't have to test if the alternating series is convergent if b sub n here is itself convergent. So that's kind of the trick here, is if we know this thing here converges, then we know the alternating series also converges, because it would be absolutely convergent. If I just look at the non-alternating part, okay, then absolute convergence gives me convergence. Okay, and so I don't have to go through, the 2 steps before. Okay, so is this thing convergent? Is the summation of the absolute value of negative 1 to the n minus 1 of 1 over n squared as n equals 1 to infinity, okay, convergent or divergent, and this is going to equal the summation n equals 1 to infinity of 1 over n squared. And so what do we know about 1 over n squared?
It converges.
Yeah, why?
Geometric series.
No, it's not geometric.
Oh, oh, it's a P series.
Yeah, it's a P series. Okay, it's a P series with n equal 2. Okay, and so since that's greater than 1, this thing converges. Which means that if the non-alternating series converged, then the alternating series we get for free comes along for the ride. And so so this is absolutely convergent. Thus, n equals 1 to infinity of negative 1 to the n minus 1 of 1 over n squared is absolutely convergent. Okay, absolutely convergent. Okay, number 3. Okay, determine if the series summation n equals 1 to infinity of uh, of cosine n over n squared is convergent or divergent. You might be thinking, well, this thing doesn't alternate, okay, but it kind of does. Okay, with that cosine n, cosine will bounce between 1 and -1, right? And all the values in between. And so if we can absolute value this thing, okay, if I can put absolute values and look at the absolute value of the series, the terms of the series.
Okay, I found this on the web for the term.
Okay. So let's look at the original series that we put up there. N equals 1 to infinity of cosine n over n squared is going to be cosine 1 over 1 plus cosine 2 over, or sorry, 1 squared, 2 squared, plus cosine 3 over 3 squared, plus cosine 4 over 4 squared. Okay, plus dot, 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 dot. Okay, so I don't know, again, this thing, the cosine on the top is going to vacillate between -1 and 1. Okay, so I know that this is similar to a p-series, n squared, but I don't really know what the cosines are doing. Okay, but I do know the behavior of cosine. And so if I absolute value this thing, cosine n over n squared, and I look at the absolute convergence, can I get this thing to be absolutely convergent? I don't know about the original. The original would be kind of hard to figure out. Okay. You know, do the cosines, how do they behave? But this thing, when I absolute value it, becomes cosine of n absolute valued over n squared, because anything squared is positive anyway. Okay, where the absolute value of cosine is less than or equal to 1. Okay, so I know that anything that cosine could be, when I absolute value it, would be between 0 and 1. Okay, it's less than or equal to 1. Okay, so because cosine is between 1 and -1. So the absolute value of cosine is going to be less than or equal to 1. Okay, so how does that help me? Well, it helps me in that now I know that all these values of cosine on the top, okay, are less than or equal to 1 over n squared, okay, which by the basic comparison test tells tells us that this thing is convergent. Because if we're always less than something we know that's convergent, tells us that the cosine n over n squared is convergent, since the summation of 1 over n squared is a p-series. P-series n equal 2. Okay, so we know that by the basic comparison test, again, let's draw a picture, that if 1 over n squared, okay, converges to the partial sums converge to some value, okay, 1 over n squared, okay, converges to some value, and the absolute value of cosine n is always less than or equal to, okay, this is the absolute value of cosine n over n squared is always less than or equal to something that we already know converges, then itself is convergent. That's the basic comparison test. And so, well, this is the absolute value, right? So now we can say, therefore, okay, since n equals 1 to infinity of the absolute value of cosine n over n squared is convergent, cosine, then the original series n equals 1 to infinity of just cosine n over n squared, because some of those are going to be negative, right? Which are going to be smaller, okay, than all of the positive values, okay, and it'll alter some of them, you know, it'll be kind of behave like an alternating series, although it doesn't truly alternate, but you know, half the terms are going to be positive, half of them are going to be negative, and you're going to get the negative ones to cancel out from the positive ones, okay, you're going to get some subtraction off. So if we made all of those positive, we now know that even if we make them all positive, it's still going to converge, and the original series will be absolutely convergent, and thus convergent, because anything that's absolutely convergent is convergent already. Okay, so it was convergent. Okay, so a lot of kind of logic, pushing logic through on that one. Okay, we said, okay, if it's, let's see if we can get the absolute to be compared to something, and we could, and therefore that the absolute values are convergent, and therefore if something has absolute values that are convergent, then it itself is also convergent. Okay, because absolute convergence is the harder to prove. Okay, let's talk about the ratio test. Okay, and this one is, in my opinion, this is the most powerful test. Sometimes it fails us, but in my opinion, this is my go-to. This is the one that I usually, if I look at a series, I usually would try the ratio test first, unless it's something that's really simple. Okay, that I can kind of pick out already. But I think this is the most powerful test, the ratio test. Okay, and it says if the limit as n goes to infinity of the absolute value of an plus 1, oops, an plus 1 over an equals some limit okay, and that limit is less than 1, then the series we should probably put then the corresponding series. Series summation a sub n as n equals 1 to infinity okay, is absolutely convergent and thus convergent. We now have a test for absolute convergence, which is kind of nice. Okay, and thus convergent. Okay. Okay, if the limit as n goes to infinity of a sub n plus 1 over a sub n equals some limit, the limit exists, okay, and it's greater than 1, then the series, then the corresponding series summation an n equals 1 to infinity. Okay, is divergent. And if the limit as n goes to infinity of an plus 1 over an equals L, and that is equal to 1, then the test is inconclusive. Okay, and so choose a different test. Okay, and again, this is my favorite test of them all because it works for a bunch of stuff. Okay, let's look at example 4 here. And example 5. Okay, so example 4, okay, says test the series summation of -1 to n of n cubed all over 3 to the nth power for convergence. Okay, does this thing converge or diverge? Or do we need to try something else? Okay, let's test this series, this alternating series for convergence. Okay. So we could use the alternating series test on this if we wanted to. But let's use the ratio test. Okay, limit as n goes to infinity of the n plus 1 term. So that's -1 to the n plus 1, n plus 1 cubed all over 3 to the n plus 1th power. Okay, that's the n plus 1th term all over the nth term, which is just -1 to the n cubed over 3 to the n. Okay, and I'm gonna flip those fractions upside down. This is limit n goes to infinity. Now of -1 to the n plus 1. Okay, over, oh, this is n plus 1 cubed, over 3 to the n plus 1 times 3 to the n over negative 1 to the n cubed. It should just be n cubed. Okay. Now let's simplify this. So this becomes the limit as n goes to infinity of negative 1 to the nth power and negative 1 to the n plus 1 just gives me negative 1. Okay, boom, boom. Okay, 3 to the nth over 3 to the n plus 1 just gives me 3. So this is just 3. So it's just negative 1/3. And then we get n plus 1 cubed over n cubed. Okay. And let's see what we can do with that. So this equals the limit as n goes to infinity of negative 1 over 3. I'm going to bring this inside. This is just n plus 1 over n cubed. Okay. And so this becomes the limit as n goes to infinity of negative 1 over 3. This becomes 1 plus 1 over n cubed. Okay, and so this thing just goes to 0. And 1 cubed is 1. Absolute value of negative 1/3 is just 1/3. This equals 1/3, which is less than 1, which tells me that this thing is convergent. Therefore, by the ratio, you have to tell me what test you used. By the ratio test, okay, this series, n equals 1 to infinity, of negative 1 to the nth term of n cubed over 3 to the n is absolutely convergent. Okay, and thus convergent. Okay, but again, absolutely convergent implies convergence. Okay, thus convergent. Okay, let's try another one of these. Let's go to number 5. Okay, let's try the summation test. The summation n equals 1 to infinity of 1 over n factorial for convergence. Okay, let's test this thing. Is it convergent or not? Let's use the ratio test. Okay, the limit as n goes to infinity of 1 over n plus 1 factorial over 1 over n factorial equals the limit as n goes to infinity of 1 over n plus 1 factorial times n factorial over 1. Okay, so this thing just equals the limit as n goes to infinity of n factorial over n plus 1 factorial. What does that mean? N factorial over n plus 1 factorial. Well, n factorial is you multiply all the numbers, all the positive integers up to n. So this would be like 1 plus, or 1 times 2 times 3 times 4 times ... times n. Okay. And what would n plus 1 factorial mean? It would mean I would go one more. 1 times 2 times 3 times 4 times ... times n plus 1. This is the limit as n goes to infinity. Okay. Okay, and so 1, 1, 2, 2, 3, 3, 4, 4, n, they all cancel out. And they leave me with limit as n goes to infinity of 1 over n plus 1, which I know that's 1 over infinity plus 1, which is 1 over infinity, which is equal to 0. Okay, and so what does that tell me? Well, it tells me that since that's less than 1, then the series is absolutely convergent. Okay, then the series is absolutely convergent. Okay, and thus convergent. Okay. Okay, let's do the root test. Okay, so the root test says if the limit as n goes to infinity of the nth root of the absolute value of a sub n, okay, is equal to L. Okay, so I take the series and I nth root the absolute values, okay, is less than 1, then the series summation n equals 1 to infinity of a sub n is absolutely convergent. Okay, and thus convergent. Okay. If the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to L, which is greater than 1, or the limit as n goes to infinity. I think we included that in the last one. No, I think it's implied. Limit of the nth root of a sub n, okay, equals infinity. Okay, so obviously infinity is bigger than 1. So if if the limit does not exist or goes off to infinity, then the series is divergent. Series a sub n is divergent. And if the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to L is equal to 1, then the test is inconclusive. Use a different test. Okay. Okay. Let's look at number 6. Here, test the series summation n equals 1 to infinity of 2 to the n plus 3 all over 3n plus 2 to the nth power. Okay, we want to test this thing and see, is it convergent? Or is it divergent? for convergence. Okay, is this thing convergent or divergent? Okay, so we have these terms that are raised to the nth power. And so we can use the root test to take the limit okay, as n goes to infinity of the nth root of 2n plus 3 all over 3n plus 2. Okay, absolute value of that to the nth power. Okay. Okay, and what that allows me to do is it allows me to get rid of the nth roots and the power of n here. This is equal to the limit these are going to cancel. The limit as n goes to infinity of 2n plus 3. This is the absolute value of 2n plus 3 over 3n plus 2. 3n plus 2. Okay. And we can use the L'Hopital's rule, or we could do this algebraically. It really doesn't matter. Okay, this is equal to using L'Hopital's rule equal to the limit as n goes to infinity of 2 over 3 absolute value, but the absolute value of 2/3 is just 2/3, which is less than 1. Therefore, the series summation n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the nth power is absolutely convergent. And thus convergent. Okay. Okay, and that's 11.6.